So, good morning, everybody. Also, people from TNO, good morning and welcome. It is, after an inspiring day yesterday, I think it's quite early. We have a long day, but also a very exciting, interesting day where all ACT projects will present themselves. And so this is a very nice opportunity to get an overview of all the ACT projects. On behalf of the organizing committee, I welcome you. My name is Jan Hopman from CATO. And these days were organized by ACT, CATO, the Norwegian embassy, and our Dutch Ministry of Economic Affairs. So welcome. The chair of the day is the how should I say, the president of ACT, which is coordinator of ACT. It's Ragnhild. So Ragnhild, the floor, everything is yours.
Thank you so much, Jan. Well, I have something with me and this system, I don't know. Welcome, good morning, ladies and gentlemen. Nice to see you here again. I hope we will have a very inspiring day. And the aim with this type of meeting is, of course, to have the latest knowledge and information from the projects. And we have asked them to be very precise and define why are they doing this work, what is the impact, and how can the results really drive the CCUS forward. The why and how will be very important. So for those of you who haven't thought about that yet, please do so. I've been told that we should be like 100 people today. I cannot count so many yet, but there are some weather problems, I was told. So I think people are waiting for taxis or something like that. So we will expect more people to join. But nevertheless, I feel privileged to stand here and say that we will really have a long and interesting day today. I will chair this meeting until lunch, and thereafter, because it's a good collaboration between Norway and the Netherlands, Gerdi will take over after lunch. I hope you will applaud that, no objections, so this has been approved. We have had a great collaboration with the Commission since we started, actually before we signed the contract. And the great guy behind this collaboration with us is Vassilios Kougionas. He is now the Senior Policy Officer at the Commission, at the DG Research and Innovation. And he has been with us and really stood up for us and taken care of us, if I could say so. He has been interested in our work and what we have delivered and the results having achieved together. So it's really my pleasure to invite Vassilios to be the main speaker of today or opening this meeting. Unfortunately, he couldn't join in person, but I know the technicians over there, they have good contact with Vassilios in Brussels. So we say hello and welcome to Vassilios. The floor is yours.
Thank you very much, Ragnhild, for your kind words. It was really a pleasure to be responsible for this great initiative, and I must say it was extremely successful in what it has achieved, and managing to have 3 calls and now a 4th one and attracting so much international collaboration was really excellent. So it's my pleasure that I'm invited to this knowledge sharing event, and it's unfortunate that I couldn't join you, but I would like to give you a presentation today of the research innovation activities that we do in the European Commission on CCUS, and of course they're linked to Horizon Europe. So if I, yeah, go to the next, no, it's the previous one, yeah. So we aim in, of course, towards clean energy transition in the EU. And this, of course, is in line with the goal we have in the EU for a net zero greenhouse gas emissions by 2050. And of course, we aim to switch fossil fuel energy to renewable and zero carbon energy. This is necessary as, of course, this represents roughly 3/4 of the EU emissions of CO2. And this transition needs to take place without, of course, hampering the environment, but also without reducing the availability and affordability of energy for all its users. This, of course, it's quite relevant to the war that's happening now in Ukraine, and of course, the Repower EU communication that we had in the Commission recently. And the remaining, of course, fossil fuel, but also most importantly, the energy-intensive industries, they need to be fully decarbonized in order to achieve our objectives. And this, we believe, can only be done through carbon capture, utilization, and storage. So what are our policy tools for CCS or CCU or CCUS? So the first, of course, the EU climate law, the Fit for 55 package, which aim for 55% reduction of CO2 by 2030, the energy system integration strategy and the hydrogen strategy. I mentioned already the Repower EU, of course, the emphasis on the security of supply and energy efficiency, but of course, decarbonizing our industry, it's also very important. The Trans-European Energy Networks, which of course now include CO2 storage, sustainable in taxonomy, which includes CCS. Everybody knows, of course, the CCS directive and the European Union, European Trading Scheme. Of course, the Commission has published in December the European Commission communication on sustainable carbon cycles. And following that, we will propose a new regulatory framework for the certification of carbon removals by the end of 2022. And the funding schemes to support CCUS projects are on Horizon Europe, the Innovation Fund and Connecting Europe Facility, and also the New Generation EU, the European Recovery Budget, and we have already national plans from the member states which include CCUS. And finally, the Strategic Energy Technology Plan, which of course has implementation working group on CCUS, and in which member states, the Commission and industry participate, and they have recently outlined the new research innovation targets in line, of course, with the Green Deal and Fit for 55. So CCUS, we think we will play a crucial role both in Horizon Europe, but also in the EU Green Deal. And this is very important for the transition of energy-intensive industries towards climate neutrality, particularly important for those industries where other alternatives do not exist. And as we know, if it is combined with sustainable biomass, it could create negative emissions. And also the low carbon hydrogen with CCUS could play a role towards the fully renewable hydrogen sources. Finally, we want to integrate CCUS in industrial clusters and also to demonstrate the full CCUS chain. And also the conversion of captured CO2 to useful products and fuels could play an important role towards clean energy transition. So we are funding research and innovation, and to expect to have impacts generated out of this, we aim to have accelerated the rollout of infrastructure, in particular for CCUS hubs and clusters. We want to continue what we had in before the project network and continue knowledge and best practice sharing activities between the demonstration projects and particularly connecting the industrial CO2 sources with bankable storage sites. And this will provide great confidence, we think, for decision makers, but also for investors. And then we want to integrate this, of course, CO2 captures, CO2 storage and use in industrial facilities to maximize the efforts and to close the carbon cycle. And this will provide actually demonstration of these technologies at industrial scale and could pave the way for subsequent first-of-a-kind industrial projects. Of course, one of the stumbling blocks is the CO2 capture cost, and then we want to reduce overall the CCUS cost and to have a wider application of CCUS. And that's why I want to develop innovative technologies for also for CO2 conversion and to reduce the need for pre-concentration and purification. Then, of course, measurement, monitoring, verifications for storage are very important in order to document safe storage. And this is also important for public acceptance of this technology. And the CDR, or CO2 removal, is becoming important, and that's why we will allocate research on direct air capture and storage and bioenergy with CCS as CO2 capture technologies in combination with CO2 storage, because we aim to develop cost-effective carbon removals in view of achieving our net zero targets. And finally, we want to assess the environmental impacts and risk of these technologies in the short, medium, and long term. So what are the topics that we have already included in the first 2 years of Horizon Europe, 2021-2022? First of all was the integration of CCUS in hubs and clusters, including knowledge sharing activities. And the total budget for that was 2 million euros. That was a CSA action. And one project will start in 2022. Then the second topic was on cost reduction of CO2 capture of new or improved technologies. And the budget for that was close to 30 million euros. And this was research innovation action. And 2 projects will start in 2022. And in 2022, we had a third topic, which aimed for decarbonizing industry with CCUS. And this was a large topic with a budget of 58 million euros. And this was an innovation action aiming for high TRLs, and to expect that we'll have 2 projects to be selected for this topic. Finally, we are in the preparations for work program 23-24 in Horizon Europe. And these topics, of course, are in consultation with member states and the program committee. And we aim to include the research innovation actions on CCUS, but also CDR, including CO2 transport, utilization and storage, but also, as I mentioned before, on DACs and BECs. So a few words about the Clean Energy Transition Partnership. The Clean Energy Transition Partnership, which was mentioned yesterday by Ragnhild, aims to empower the energy transition and contribute from a research innovation perspective to the EU's goal of becoming the first climate neutral continent by 2050. But CETP, it's important to say that builds on the set plan implementation working groups, and particularly for the energy relevant ARANETs. So the activities of the very successful ARANET, ACT ARANET initiative on CCUS will of course continue under this CETP, and under this transition initiative 3 from the CETP partnership. So we really hope that we'll see the same momentum and motivation as we have seen in the ACT ARANET, but also we're hoping to see the international cooperation as active as it was in ACT ARANET, which has managed to attract funds from India, US, and Canada. So the opening of the call is expected, as was said yesterday, in September 22, and the CTP grant itself agreement has a fixed starting date on the 1st of May 2022. Now I'm going to say a few words about the new mission, the phase 2 mission that was established under Mission Innovation, the CO2 removal mission. As was said yesterday, the ACT ERANET has contributed a lot to the phase 1 mission on Mission Innovation, the Challenge 3 on CCUS. So this actually continuations of that is the CDR mission, which this mission has an objective to enable CDR technologies to achieve a net reduction of 100 million metric tons of CO2 per year globally by 2030. And we really hope that members of this mission will collaborate with ACT, ERANET, or with under the CTP to continue the international multilateral collaboration. So the scope of this mission is technological CDR approaches, which include direct air capture, but also with storage, biomass with carbon removal and storage, and also enhanced mineralization. And the emphasis, of course, of this mission is to have secure CO2 storage and also to convert CO2 to products, but to which they have a long-lived duration. The activities of the CDR mission are expected to be methodologies for life cycle analysis and techno-economic analysis, but also research development and demonstration for lower TRLs, CDR technologies, and for high TRLs, and also the lessons learned from the first generation CDR projects and business models. The mission has, these are the members, and they have 3 colleagues from Canada, Saudi Arabia, and the United States, and the members are Australia, the European Commission, so DG Research Innovation represents that, together with DG Klima, and then India, Japan, and Norway, which is a core member of this mission. And then there is an ongoing engagement of this mission with industry, the innovators, but also with academia. So the next steps of this mission is to finalize the innovation roadmap, which is already ongoing, and the feedback from member states has already been received. And what is important to note here that within the ZEP TIP, the Zero Emission Platform, there is a specific subgroup that was established on mission innovation, and they provide help and advice to the European Commission on these activities. And then following that, there will be a mission action plan, and the final result will be a co-design projects with members and partners. So the next important event will take place in Pittsburgh. This will be a ministerial event, and we're already looking for flagship projects, or they call them sprints, which will be presented at ministerial level, and they will make a difference on these technologies. So this is information on the mission innovation that you can find on this website, but also you can contact, if you are interested, the Stephen Clark, who is the Secretariat for this mission in Canada. And this was my last slide. I would like to thank you very much for your attention. I only have 10 minutes, of course, and I would be happy to reply to your questions. Thank you.
Thank you so much, Vassilios, and thank you for putting up expectations also for us to be successful in the years to come, and that well, we need to rely on the researchers and the industry to put their forces together to come up with the good results. Thank you so much, Vassilios. I hope you can join us for the rest of the day, or at least some of the day, and listen to the presentations to come. Actually, we are now like 10 minutes ahead of time, which is really, really good. Are there any immediate questions for Vassilios? We take the time for a couple of questions. I don't see any hands. Yes. Oh, now it starts working. Over there. There was one close to the pole over there.
Thank you. Jon Sletten from Yara. There are some discussions about cost level for the CCS. What is seen as an acceptable cost level going forward? What is believed to be achieved on the cost level?
Vassilios, could you hear the question?
Yeah, I mean,
thank you.
Yeah, of course, the cost level, of course, is not. I mean, within our programs, it's not really mentioned as such. Of course, the price of carbon, of course, as you know, provides a good indication of or result that with the price of CCUS at the moment, we could soon go to maturity, to market maturity, and start deployment. But I think this has to be judged for CO2 capture together with storage and transport, and it depends on the particular situation. So in our programs, we don't give a particular indication of the cost that is desirable. Yeah.
Thank you. And the next question here in front.
Thank you. Pierre Serassi from Sintef, Norway. Just a clarification question about the CET partnership, and maybe to you, Ragnhild, the Act 4. Is the meaning that the two will merge afterwards, or is it two separate programs?
I can answer that question. You ask whether the Act 4 is separate from the CETP. There are two routes. Yes, they are. They are not combined. You want to add something, Vassilios?
Yeah, I mean, as you said, they're not combined. I mean, you mentioned yesterday that the Act 4, it's a call from a few countries, but it's good that we see this international cooperation within it. And I mean, the CETP call, of course, will be a different one. But as I said, we really hope to attract the same international cooperation as we had the privilege within ACT.
Thank you so much. Since we are ahead of time, I just want to ask the funders to stand up. Unfortunately, we don't have all the funders here today, but they are joining virtually. So all the funders, just say who you are and which organization you represent, because that might be important for the projects if they want to connect with you.
My name is Gerdy Breenbroek from Netherlands Enterprise Agency.
My name is Kari-Lise Rørvik. I'm from Gassnova, representing Climate.
Good morning, I'm Lee. I'm colleague of Geerty from RVO.
I'm Peter from RVO, a colleague of Gerdy. Lee.
Good morning, everyone. My name is Amishi. I'm here from the USD Department of Energy, and I'm representing the Carbon Management Office, which is capture, storage, and utilization.
And then we have Hanifa over there. Yeah.
Thank you very much and good morning, everyone. My name is Hanife. I'm working at Technological and Scientific Council of Turkey. It's meaning shortly we say TÜBİTAK from Turkey. Very nice to meet you. Thank you.
So did we miss anyone? I don't think so. But now you know the faces, and those being here in person, you're welcome to contact and whatever question you might have from the projects. They will answer the questions accordingly. So, but we say thank you to Vassilios and move on to the next step. We have, as you have seen from the program, we have bulked the projects, and it will be a rather intensive period now. There are like maximum 15 minutes for each of the projects. And when it's close to 50 minutes, I will stand up and give indication that you need to stop. If you are finished before 15 minutes, of course, there will be possibilities for questions and interactions. But let's kick off with the newest project. It is dealing with the negative emissions in the waste-to-energy sector, and it's a pleasure to welcome you. Matja, you're already on your way, so please.
Okay, good morning. Can I use the pointer? Okay, yeah, so good morning. My name is Mathieu Lucieux. I'm a professor of clean energy with CCS at the University of Sheffield, and I'm the coordinator of the newest project. So we're looking at negative emissions in the waste-to-energy sector, and we're trying to advance the tier level of CO2 capture technologies in that sector, and also looking at the potential for negative emissions in Europe from the waste resource. Okay, so it's a 3.5 years project. We have 6 partners from 4 countries. So partners in 4 partners in the UK. So the University of Edinburgh, where I was based before, the University of Sheffield, where I am now, the Scottish CCS Centre, Carbon Clean, which is a CO2 capture solvent technology developer, SINTEF in Norway, the University of Stuttgart in Germany, and TNO here in the Netherlands. I've got a budget of 2.5 million euros and an expert advisory group of about 30 members that ensures the, if you like, the industrial relevance and the relevant society of our research program. So they're part of our strategy for user engagement. So you can see the list here. We have a balance of end users, technology developers, trade associations, regulatory body, environmental agencies in the UK, Netherlands, and some university in China and an energy utility in the UK. So we are in the final year of the project. So just to point out that we've completed some of the activities, and some of them are ongoing, and we're aiming to finish in February 2023. And this is the, if you like, the technical program. So we have a work package on engagement, and this is the, if you like, the research activities. So we are looking at advancing the TL of oxyfuel and membrane technologies for waste-to-energy plant. We are looking at retrofit and new build solution with solvents. So here we're doing pilot scale testing of 2 solvents at 1 ton a day scale and 10 ton a day scale. And finally, there's a work package doing a comparative assessment of these technologies for the waste-to-energy market, and aiming to quantify the negative emissions in the waste-to-energy sector. So why are we interested in waste? So the waste resource is expected to grow globally. There are projections for having in operation 2,700 waste-to-energy plants by 2027, and you can see on the right-hand side that every segment of population income is expected to produce more waste in the future, and also people are, if like in the world, are expected to move from lower to lower middle income, and therefore producing more waste. Half of the global waste is basically composed of biogenic carbon. So if you add the on this pie chart, the food and green, paper and cardboard, wood, rubber and leather, you end up with more than 50% of the resource being biogenic. So that's relevant because if you capture the CO2, you create a form of BECCS, form of negative emissions, form of biomass energy with carbon capture and storage. So, and this is what we're doing here. So we're trying to quantify the net climate benefits of waste to energy with CCS. So this is quite a packed slide, but if you focus on the right-hand side, we're trying to quantify the net climate benefit, and that's composed of two components. So we have the direct greenhouse gas emission reductions when you do waste to energy with CCS. So you capture the fossil carbon in your waste stream, and you also avoid emissions by burning waste in a waste incinerator instead of sending to landfill, and also through the recovery of metal and other resources in the, for example, in the ash from combustion. So you avoid the greenhouse gas emissions of producing those metals, for example, and also you displace other forms of energy generation, heat and electricity. And then the second part is carbon removal. So this is the biogenic carbon in your waste that has to be subtracted from the greenhouse gas emission of the CCS chain, but when you add them together, you still have a net climate positive contribution that we call a carbon removal. And so this is why we're doing this. We're looking at removing CO2 from the atmosphere from waste to energy with CCS. And one thing that I'm going to point out is in this project, we're focusing on having zero residual CO2 emissions from CO2 capture. So we're looking at capturing 100% of the CO2, or demonstrating that you can capture 100% of CO2 that's coming from the combustion of waste. So some numbers. So on the vertical axis, you have the climate change impact of different types of plants. So left-hand side is a waste energy plant producing electricity without CCS. So the orange bar is the direct fossil CO2 emissions from the fossil carbon in the waste. And then below the line, below the zero line, it shows you the displacement of energy, the recovery of material, and the avoided greenhouse gas emissions. When you add CCS, you basically abate the orange bar, and also you create this negative emission in blue. And we think that for a UK plant, the climate change impact goes from 340 kilogram of CO2 per ton of municipal solid waste to minus 535 kilogram of CO2 per ton of municipal solid waste. The right-hand side, you have two cases looking at combined heat and power. So if you're producing heat from your waste to energy plant, you increase this climate change benefit to potentially 774 kilogram of CO2 per ton of municipal solid waste. So this is for a UK plant, and we. Oops. This is for a UK plant. Obviously, this is European specific, and that's what we are assessing in the rest of this project. We think that as we decarbonize electricity and heat, that contribution is going to reduce because the avoided impact of replacing zero carbon electricity are going to be zero or zero carbon heat. What's happening here? Okay, so now I'm going to talk about the work on demonstrating the technology at pilot scale. So this is work taking place at the University of Stuttgart. This is a summary of their research results. So they're looking at demonstrating at 200 kilowatt scale, so TL 5 and 6, the oxyfuel combustion of what's called solid refuse fuel. So this is waste that is sorted, and you focus on the higher calorific value part of the waste. So this is, if you like, the good part of the waste that you burn into an oxyfuel environment. They've got this pilot plant where they're demonstrating that you can achieve stable combustion in a circulating fluidized bed. And they are basically testing different types of oxygen environment. They're looking at the production of NOx, chloric acid, and how you can achieve a stable combustion. Then they're also developing a model in a process modeling software called Aspen. So they're effectively modeling their pilot plant and then using that to scale up the results to a large-scale facility it's got a capacity of 133 kiloton of CO2 per year. Then this is work done in Norway at Sintef. So here they're interested in the fundamental of combustion of municipal solid waste. So they have an experimental setup on the right-hand side where they effectively burn a small pellet of waste, and they look at the combustion properties in different oxygen environments. and this is then used to inform full-scale plant simulation by CFD, computational fluid dynamics. So you're looking at how combustion takes place in what's called a great furnace, which is the combustion technology that's the most used for waste in air and in an oxyfuel environment. And they also do work on membrane. So this is process simulation, looking at how you can implement membrane technology specifically to a waste-to-energy plant. Then we have work here taking place here in the Netherlands. So this is TNO testing carbon clean solvent in a 10 ton of CO2 per day CO2 capture facility at a plant called Twents. So it's like a commercial plant that's been upgraded for testing the solvent. We achieved 2 months of operation, and the demonstration is currently ongoing. And the key here is to de-risk carbon clean solvent and to propose a solvent management strategy. So how you can maintain the health of your solvent when it's exposed to the low-level combustion impurities from the combustion of waste. Then we also have a smaller pilot scale, 1 ton a day, at the University of Sheffield. And here we're focusing on understanding the effect of trace metals and combustion aerosols from waste on CO2 capture solvent. So on the bottom right, there's a picture of a waste boiler. So we're going to burn this summer two type of different waste wood, and then measure the aerosol from combustion before and after the CO2 capture plant. We're going to be testing a reference solvent that's commonly used to benchmark CO2 capture technology, so it's called MEA, and we're also going to be testing carbon clean solvent. The tests are planned for July and August, and we're really focusing on these trace metal aerosol particulates to characterize their impact on emissions into the atmosphere from the solvent. This is all the process analytical equipment that's been commissioned so far, and we're hoping to start in July, August, the testing. And now going back to, so we can roll out these technologies, but at the end of the day, what's the potential for negative emissions? So this is preliminary result from the project. So we've looked at what would happen if you were able to retrofit all the existing waste energy plants in Europe with CCS, country by country. So on the diagram here, you have the potential for negative emissions in every country. So the dark green bar are the existing plants. The stripy bars are the capacity that is not being used, so the waste resource that is still going to landfill. So there are countries that have basically not sending anything to landfill, and there are countries that are sending a portion of their waste to landfill. So you can take the example of the UK here. So you see that we could actually do more waste to energy recovery. And then on the right-hand side of the diagram, you have the orange bar. These are the countries that are currently sending all of their waste to landfilling and not doing any waste to energy and not doing any CCS. So if we're able to retrofit all the existing plants, so this is the cumulative dark green bar, we think we could achieve 50 million tons of CO2 of carbon removal in the sector from municipal solid waste. And if we can divert the orange bars, the waste going to landfill into waste energy CCS, we could have another 50 million tons of carbon removal. This number is likely to be underestimated. It doesn't include the avoided emissions when you divert landfill from landfilling to waste to energy. It only includes the biogenic carbon. And also, it doesn't include industrial waste. It only includes municipal solid waste. So we think that the resource could be more important, but we find it very difficult to get good data on industrial waste. And so this is what we're going to do in the last part of the project now. We're going to add some more granularity to this number and basically develop a method to provide a better estimate of the negative emission sector, mapping existing waste energy facilities in Europe, the access to CCS cluster, space requirement, what is the resource, how much biogenic carbon is there in waste, it's country dependent, it's income dependent. It will also depend on the implementation of waste management policy and recycling. So we're trying to do that in the last part of the project. Okay, so what's the case for waste energy with CCUS? And this is where I'm going to finish. So we think that it's possible that in a carbon-constrained world in the future, the value to society of waste may actually be its biogenic content, and that the negative emissions in waste may become a strategic resource to countries to meet their carbon removal target. It's a form of BECCS, but unlike conventional BECCS, there's no impact on food security or land viability because you're burning waste, so you're creating BECCS from products that have already been discarded, if you like. And then how can we move forward in the 2020s? So we need to de-risk these technologies. Waste is a challenging fuel. It produces combustion impurities more than other fuels, so we need to do long-term testing. We've managed to achieve a few months of operation in this project, but we need to go beyond that. There's evidence that CO2 capture solvent, for example, needs to be tested for at least a year to provide representative results. We need to show that we can use CCS to achieve zero residual CO2 emissions. So we aim to demonstrate that you can capture 100% of the CO2 coming from the waste using CCS. So zero residual emissions with CCS so that you can provide maximum value. And we need to value the embedded negative emissions at local and national levels of our waste. So one thing that's currently missing is the reporting of biogenic emissions from waste is very patchy. It comes from the fact that in many countries, waste energy plants are excluded from the EU ETS. And we need to have business models that are suitable for waste energy plants. So, for example, in the UK, the business models for waste energy plants with CCS exclude the monetizing of negative emissions at the moment. So it has to change if we're going to roll out this technology in the sector and provide maximum value to society. And we need to understand the public acceptance. So the public acceptance of waste to energy is different to the public acceptance of CCS, but it's possible that when you put the two of them together, you might actually create a win-win, create artificial trees basically from our waste. So I think there's a lot more work that needs to be done in this area. So this is how we move forward. This is my last slide. We have a newsletter. You can join us, follow our project, and yeah, we'd like to acknowledge the funding from ACT. Thank you very much.
Thank you so much. I think you've nearly used your time, but we'll take one quick question. Okay. Is there a question in the audience? Yes, Sevket, he has one over there.
Hello, Joseph Kevis from CERT. Thank you very much. Excellent work. I have one question which may become two. You refer to carbon clean solvents. What exactly is this?
Oh, it's the name of the company, so they call carbon clean.
Ah, so you're not talking about the solvents you're using are not carbon clean.
No,
in the sense
no,
that
sorry. This is sorry.
Okay.
This is how they market their technology. It's called carbon clean. Yeah.
Okay. All right. Thank you. And if I missed it, you refer to membrane technology, right?
That's right. Yeah.
What kind of membrane technology exactly is it?
I couldn't possibly answer. I think we had a when we started the project, initial plans of using proprietary technology, but I think we've gone back to I think generic technology. I can put you in touch with my colleague at Sintef if you're interested. Yeah.
Thank you. Sorry for calling you Sevket, George. But we have Sevket over here. He is the next presenter, and now we will have some kind of interesting collaboration between the CCS and the geothermal, Turkey, UK, Iceland, and more to come. So please take the chair.
Thank you.
Good morning again. I have a couple of short videos, so we had to run from our own computer. Ragnhild, thank you very much. Our project, as Ragnhild mentioned, is a combination between CCS work and the geothermal energy. And our partners, we have 8 partners, funding of about 2.2 million euros. 2 partners from the UK, Imperial College and CLCombustion. From the Netherlands, Seismic Mechatronics and Technical University of Delft. From Turkey, one of our industrial partners, Zorlu Energy, geothermal site, and the Middle East Technical University. And 2 non-funded, non-ACT countries at the time of, for the case of Italy, obviously, OGS at the time of Act 2, and Reykjavik Energy, which still is not member, but they are funding their own activities. What are our objectives? Geothermal energy, it actually, contrary to knowledge or assumption, produces and emits significant amounts of carbon dioxide to the atmosphere. And the role of carbon dioxide in geothermal production is actually a positive effect in a way that the partial pressure of dissolved carbon dioxide in the geothermal fluid helps produce at an accelerated state the geothermal fluid. However, the non-condensable gases that are in the produced fluid are separated and emitted to the atmosphere. Over time, the geothermal production also re-injects the spent geothermal fluid, which is obviously without the carbon dioxide in it. And over time, this dilutes the level of carbon dioxide, therefore the phase and the source of pressure in the geothermal fluid. Therefore, you have a decline in terms of carbon dioxide concentration and decline in the pressure that drives the production. So the objective of our project is really look at this process and how we can utilize CCS and CCU technology to both store carbon dioxide but also enhance production, or at least maintain production over a long period of time. We have 2 different structures geologically, carbonates in Turkey and basalts in Iceland. You will know about the Carbfix 1, Carbfix 2 projects. Carbfix has gone commercial now, serving as storing carbon dioxide on their sites. So we are looking at the behavior of the structures in terms of reaction and geochemistry, as well as response to injection of both carbon dioxide and non-carbon dioxide fluids. In terms of technology, we are looking at monitoring the performance of injection using distributed acoustic sensing technology, as well as the monitoring source, EM vibro source, that is newly developed by Seismic Mechatronics. And to follow that, obviously, we have some numerical modeling of the performance and looking at life cycle and techno-economic impacts and assessment of the application of the technology, mainly focusing on the Turkish side, the full Büyük Menderes Graben, because there are about 30 companies that are operating within a 300-kilometer zone. I have quite a lot of slides, but I'll just fly through them to save time. The 2 sites, both the Helşehide site in Iceland and the Kızıldere site in Turkey, are high-pressure, high-temperature areas, and they are some of the largest producers, geothermal energy producers in the business. So when I refer to the Büyük Menderes Graben, we're actually looking at an extension from Denizli all the way to Izmir or Aydın, and we're looking at the techno-economics of implementation of the technology there. We've done some fundamental work looking at PNS wave behavior of the structures, looking at basalts and the carbonates from Kızıldere. And these data later have been used in the performance assessment when we do the seismic surveys. At Technical University of Delft, our colleagues are looking at the behavior of injected fluid, both supercritical or dissolved CO2 using a large-scale borehole simulator, taking samples of about 40 centimeter diameter, and also characterizing the seismic velocities and changes, especially through fractures and flow through fractures. At Imperial, we are looking at long-term work and treatment of both the basalts and the carbonates in our reactors, characterizing pre- and post-process behavior, both from reservoir properties and mechanical and elastic properties. So we have a couple of reactors. On one side, we have the Hilişehir basalts. On the other side, we have the Kızıldere carbonates. And some numerical model and geochemistry modeling has been done to actually generate the synthetic brine with CO2 to set up the experiments. And these have been running from about July 2020, soon after the pandemic. Our field work on the sites, if we look at the Kızıldere site, we have about 7,000 tons per hour production from 41 wells, but we have 27 wells injecting non-CO2 reservoir fluid back into the reservoir. If we look at the site, the oldest part, which started production in 1984, is to the northeast, and that is the shallower part, and the production has moved over time further deeper, moving into higher carbon dioxide concentration zones. And in these areas now the pressure, the carbon dioxide level is dropped down to about 0.1, 0.2%, and the pressure is gone. So they have to start using pumps unless we can enhance the pressure again with the injection of carbon dioxide. So that's the area that we're looking at injecting the carbon dioxide. We've looked at selecting our wells for injection and monitoring. So the old production well, R2, where they are injecting about significant volumes of spent CO2, is our injection well. We have 2 observation wells, which we will be installing engineered fiber optic cables. And these are selected because they are, when they have done some tracer tests, they are in the path of the flowing fluids. So a helically wound cable, which later I will show, will be installed in an L shape between the wells, and then that will be connected to the fiber optic cable that is put into the wells at about 950 meters depth, and then the seismic monitoring or performance monitoring will start. The work at Kızıldere had been affected by COVID significantly. We didn't do much field work there and concentrated most of our work at Iceland, which almost had no COVID impact over the years. We also had a few problems in terms of funding. The Turkish budget was depleting over the years as we were not able to spend much in the early years. But eventually, Zorlu Energy actually moved in and invested about 300,000 euros into a compressor system so that we can actually achieve the pressures that we are requiring and start our injection in the field. The work in Iceland, which naturally was already injecting carbon dioxide through the CARBFIX program, had started before we started our project in terms of injection. So in November 2019, we had a field survey. We looked at the injection wells. We have a number of injection wells that are injecting spent geothermal fluid here, and one of them is the carbon dioxide injection well as well. So we've selected our helically wound cable route. The blue line is the helically wound cable that we had installed 1.5 kilometers long, and also a tactical cable to our control center. I have a very small video. So that happened during the summer of 2020. Our colleagues from Silixa and ourselves went. That's the start of the point right at the top of the hill, the termination of the I will run pretty fast on that so that you have an appreciation of the terrain that we have installed the cable. And that cable was installed all the way down to somewhere around here where we have our control cabin. There is a direct air capture plant in here, an algae plant in there, and then the power station down there. So it's a complex of CO2 capture and storage site. And that's our little cabin and our colleagues from Silixa and TU Delft Mechatronics. We have done our first seismic survey. After the background survey that we have done in 2020, we've done it last summer. And that is our cable. And what we have done is we're very fortunate to borrow about 150 smart solar geophones from another project in collaboration with them, the Deepen project. And we helped them to do some active seismic surveys in their field, in the other geothermal plant that Reykjavik Energy operate. And we laid those all along our cable, plus some geophones that TU Delft brought in. So we had a system of DAS cable as well as 2 different geophones to use them to actually calibrate the response of our helically wound cable, the DAS cable. And we've run an active survey and a passive survey at the time. So that's our EM vibrator, vibro source. Moving up the hill, and every station every 40 meters. We had solos every 20 meters, every 10 meters, the TU Delft geophones, and then the solos, the cable running all the way. Obviously, they have different resolution. If the sound works on this one, oops. So the vibro source moves along the cable, and at different frequencies, we have about 16 shots at every point. So that took us about a week to go up the hill. We have a second survey, so the time-lapse survey planned for the period at the end of this month in Iceland. Everything is shipped over again. And the first background survey in Kızıldere will be done in October. Our colleagues at OGS in Italy evaluated the active seismic data, the information that came, the data that came from the laboratory work was evaluated. They've run a number of models, eventually calibrated the model with the PNS wave velocities, and compared the sources and eliminated the noise. They've started doing some tomographic inversion, and the predicted and the picked values are coming pretty close now, and characterization of the subsurface. And we have some more work to do on the analysis of this data and then implement that learning from in Kızıldere. We've got some microseismic work. I will have to move on these, and then maybe we can have these on the ACT website for everybody to see. The modeling of the work at Kızıldere, so we have calibrated our Kızıldere model now, both in terms of the pressure changes, production, and CO2 levels, and that are relevant also to the work in the laboratory that we are carrying out. And our life cycle and techno-economic work is continuing. And to complete, I would thank all our sponsors. Some of our sponsors are here in person. Thank you very much.
Thank you so much, Sevket. This is real field work you are doing.
Partly field work,
yeah.
partly lab
and
work,
extremely much technical information. Unfortunately, we don't have time for question right now, but you invite people to contact you, and everything will be on the web also. We will now move over to another very interesting industry sector, the cement sector, hard to decarbonize. I welcome Cynthia Kougionas to the stage. Carbon capture in the cement industry.
Yes.
Thank you.
So, okay, let me check. Is this the pointer? Yes. So, hi everyone, I'm Cynthia Kougionas. I am a PhD candidate at the University of Stuttgart, and on behalf of myself and Jörg Meyer, the head of our department, and partners of ACOSEM, I will show you the goals and achievements we have reached so far in ACOSEM. I'll try and go fast to keep some time for questions. Exactly. The main goal of ACOSEM is to decrease the carbon dioxide that's coming from the cement industry. So I think, like a lot of you know, for the cement industry, 1 ton of cement produces around 0.7 tons of carbon dioxide. And 2/3 of this carbon dioxide is a result of the limestone decomposition, and the rest is a result of the combustion process. To achieve the reduction, there are some very known measures that have been set by the IEA, for example, and also experts in this field, and they are mainly the decrease in thermal efficiency, switching the fuel to alternative fuels from fossil fuel, and also, very importantly, where am I? Carbon capture, exactly. Without carbon capture, it is not possible for us to efficiently decarbonize the cement industry and reach sustainable levels, and also keep almost 1 million jobs in the cement industry Europe-wide. We have 11 partners in the ACOSEM project. We come from 5 European countries. We have academic researchers. We have end users, like the cement industry involved, 3 big cement industries, and we have technology providers. Our project started in 2019, end of 2019. We have 3 years. We are quite ahead in our work. We also have 6-month extension because of the COVID pandemic and the delays that we had, but I think we're good on our way. To show you the main concept, or what we want, I can show you here. We have a conventional cement industry where you have air, all your mill, and then we produce carbon dioxide in our flue gas with around 30%. Once we move to a first generation or retrofitting oxyfuel technology in our cement plant, we move to the second one here. And we feed pure oxygen, recycle our flue gas, and have around 80% carbon dioxide in our flue gas. And then also moving on to new build plants, we remove the recirculated flue gas. We have pure oxygen entering into our cement plant and produce a flue gas that is 90% concentrated with carbon dioxide. This is the main aim of ACOSEM. What we want to do is lower the carbon avoidance cost by applying oxyfuel technology on first and second generation, so retrofit and new build plants. For that, we have done some studies on using 100% alternative fuels, and also studying the burner technology using 100% oxygen to reach negative carbon dioxide or bio-CCS conditions. For first generation plants, we have used boundary conditions from the cement plant. One of them was the Holcim plant in Legadorf, and the second one was the Heidelberg cement plant in Slite. For that, we have done design optimization and techno-economic studies, so retrofitting it with oxyfuel. And for second generation, we have also done experimental tests and analytical tests of using the oxyfuel technology, thus removing the recycle flow and so reducing the potential energy demands and the capex and the opex. This is the build of our project. I'll skip this one and go straight into the results from Work Package 2. In Work Package 2, we concentrated on the kiln burner. In the kiln burner, we have a 500 kilowatt pilot scale at the University of Stuttgart, where we could do tests with 100% alternative fuels. This was to represent the first generation or model the first generation kiln burner. In this case, we had SRF, for example, as one fuel, which we received from Heidelberg Cement. You can see all three fuels are around 10 grams. You can see the difference in the fuel and what we tested, and we used different oxyfuel conditions. So when I say oxy 31 or oxy 37, for example, that means that percent of oxygen entering as our inlet gas, and the rest is carbon dioxide. And then we also tested some wood combustion and sludge combustion, which we received from Holcim, and these are all kiln-grade fuels. Some of the results I'll show you in the next slides, because we used these then to also verify some simulations. At the same combustion chamber, so the 500 kilowatt combustion chamber, I tested combusting with 100% oxygen, so the only inlet gas was oxygen. I did a reference case with air, and you can see it right here, where the flame is kind of separated from the burner itself. Then we also used some oxygen in excess, so the L234 that you see is the excess oxygen to fuel ratio. You can see that the flame gets brighter by increasing the excess oxygen, and also wider. You also see some of the temperature profiles that I've shown here going down the flame. This is the flame center, and you see the black line, which is with the most excess oxygen, so we have lambda 4 there. That's where we decrease the flame temperature, and we see that we can actually not only run the combustion chamber with 100% oxygen, but also decrease the temperature to acceptable amounts, or to a level that is that with air combustion. So these are the simulations, the CFD simulations done by CERT, using or verifying it with the data from the University of Stuttgart. The orange line is the experimental data with SRF in Oxy 31, and the blue line is the experimental line. I think you can see, although we had quite inhomogeneous fuel, we had a very nice simulation so that we can upgrade then or upscale this process with 100% alternative fuels. Moving on to work package 3. In this work package, we were focused on the calcination process in the calciner and the evaluation of moisture and impurities on the calcination process, also in oxyfuel conditions. And one of the main results that we have found is that, yes, moisture does have a positive effect on the calcination degree, but we also have found a threshold. So I think you can see here in this graph, you see the threshold where we had 20% oxygen, 20% water, and that is where the threshold is. Any more moisture does not lead to a higher calcination result. Moving on to work package 4, this is the work package that concentrated on modeling and designing first generation or retrofitting the cement plants using the boundary conditions of the Lägerdorf and the Slite plant. We chose these two plants, or the cement industry chose these two plants because of the main difference in the raw material, which is the moisture content. In Lägerdorf plant, it is a semi-wet process. We have around 20% moisture in the raw meal, and for the Slite plant, there's around 2 to 3% moisture in the material. Here you can see that it has an effect on the design considerations. So for the Lägerdorf plant, they had to integrate a raw material drying process, whereas in the Slite plant, the main constraint is the space available for retrofitting it. So the management of impurities, especially the DSOx, was the design consideration that they took into account. It was observed from the process simulation that both plants could reach around 80% carbon dioxide in the flue gas, which is one of the first slides that I show you, and which is what we were aiming at. And from that, then I'll focus here, the emission reduction potential. We saw that we could, in this case, reach near zero emissions and 95% capture rate of carbon dioxide in the cement plant, and also that it was possible to reach negative CO2 emissions, taking into account the use of alternative fuels and the biogenic carbon dioxide. In work package 5, we were focused on the study of the new build plant, so applying the oxyfuel technology on a new build plant. In this case, we had no flue gas recirculation, pure oxygen entering. and we had a decrease in the gas flow rate almost to half. In this case, VDZ designed 2 configurations for a new built plant, and has shown that has used these configurations to find the most optimal heat integration in the plant. The main results have shown to now that the thermal energy demand strongly depends on the preheating of the material. It also shows that in one of the configurations, or in the second configuration, they included an air stage preheater, which is completely separated from the oxyfuel part. It is sealed off, and it does increase the efficiency of the plant. And it also shows that it does have a slightly lower energy demand than in the first generation or in retrofitting a cement plant. In work package 6, this is the last work package, but also a very important work package. It was concentrated on the life cycle assessment. A big part of the results have already been published. It is open access. This is the name of the paper, and there you can see the results of the LCA for the first generation, so retrofitting the cement plant in oxyfuel conditions with alternative fuels that have a high biogenic share. And the paper is quite detailed, but this is one of the results that were shown. So they did focus on the impact on the climate change, the human toxicity, and the fossil depletion potential and water depletion potential. And this is one of the results here, where we see a high share of biogenic fuels. You see also both plants, so they used the boundary conditions from Legerdorf and Slite, and have shown that there is a trade-off between the electric mix that is now and the effect on the climate change. Although, to be fair, in the future, and taking into account alternative fuels like hydrogen and water electrolysis, this should not be an issue and it should be compensated sustainably. So just a quick looking forward, the data from Akosem is not only used for these 2 plants, but for example, Heidelberg Cement and Holcim are using the information and feeding it into industrial scale projects that are coming up, like the CI4C and the Westküste taking place in Makelstetten, Germany, and the north of Germany, which are then trying to come up with oxyfuel plants. Exactly the next steps we have until March 2023. The next steps are to finalize our data, analyze them and disseminate them. Also plan a workshop that will be in collaboration with the Annika project later on, and have all our data online for the researchers and the experts in the field. Yes, thank you for our funding agencies from all 5 countries, and here are some contact information. Do I have time for questions?
So much. I think we have time for one question. Great. There's one in the back. Great project. Thank you. Excellent.
We're very proud of it.
Good morning. Yeah.
Good morning.
Well, a lot of industries are intending to use biomass. Now, in the case of cement and your trials, how much biomass do you consume per ton of cement, and what would that mean as a global volume for Europe?
If I'm not mistaken, this information should be in the paper I showed. But what I used, for example, for the kiln study, it was 100% SRF, and then I did use 100% wood and sludge. That is high biogenic shares. I think the shares of fuel that will be used in the future, and even the next 2 years in the cement industry, are unclear. The change has been significant. I mean, they moved from 100% fossil to almost 80% alternative fuels only in the last 5-10 years. I don't think I can give you a correct answer, but there should be some indication in the paper that I showed. I hope that answered the question.
Okay. Thank you so much.
Thank you.
You can provide more details later on.
Yes. Yeah. Thanks.
Thank you so much. We move further on. And now the last project in this session. Behind LOUISE, there is low-cost capture of waste-derived fuels. And I welcome Jochen Ströhle.
Okay. Thank you very much, Ragnhild, for this kind introduction. My name is Jochen Ströhle. I'm the coordinator of the LOUISE project. I'm a senior researcher at the Technical University of Darmstadt. And the name of the project is a low-cost CO2 capture by chemical looping combustion of waste-derived. Maybe I have to, okay, thank you. So we already heard a little bit about waste, CO2 capture from waste, so a lot of what has been said is also valid for this project. And yeah, but we are looking at a novel technology, that's chemical looping combustion. And the overall aim is to bring this technology to, let's say, pre-commercial demonstration or prepare for a pre-commercial demonstration, the size of around 10 megawatt power. And what's necessary is that to reach this, is there a pointer? Okay. Is to do some pilot testing here, also to prepare a basic design of such a demo plant, and finally also to prepare business cases to enable the end users also to invest in this technology. Okay, I shortly explain the chemical looping process because some of you may not be so familiar with it. So we are actually, I can, so I can also, okay. So we have, in the chemical looping process, we have two reactors and we are using a metal oxide to transfer oxygen from an air reactor to a fuel reactor. So in the air reactor, we oxidize metal oxide with air, and then the oxidized metal transfers the oxygen to the combustion process. So in this case, it's kind of oxyfuel process, but we don't need an air separation unit for this, so it's quite, has a low energy demand. The conversion in this fuel reactor is usually not 100% complete. That's why we still need a little bit of oxygen to convert the remaining unconverted gases. Yeah, we are working at a rather high temperature level, around 900 to 1000 degrees Celsius. So we can use all the heat which is generated in this combustion process for the power production and for the heat production, as in typical waste-to-energy plants. And a part of the off-gas from the fuel reactor, which consists mainly of CO2 and water vapor, is recycled to the fuel reactor to fluidize the fuel reactor. So we are using two fluidized bed systems. So this is a system of coupled fluidized bed, and the CO2 and water vapor is used to fluidize this reactor and also to gasify the waste before it can be converted by the metal oxide. Then, yeah, we need, of course, gas processing unit to purify the CO2, and then we have, we are investigating two options here. The one is, of course, the storage to have a sink of CO2. That's mainly like Norway is looking at this option. Other options is the CCU, the conversion of the carbon dioxide to valuable products like methanol or synthetic natural gas. And there we have some synergies. For example, when we have an electrolyzer for hydrogen production, some of the oxygen which is used there can also be, which is produced in the electrolyzers, can be used in the process for the post-combustion. Yeah, we have some advantages of this technology compared to others. That's rather low cost of CO2 capture because the capture is inherent in the process. So we don't need to spend extra energy to separate the CO2 from the flue gases. And we have the metal oxide working as an oxygen buffer, so the boiler efficiency is rather high. Then one problem is always with waste, that it includes a lot of substances which are problematic, forming corrosion, slagging, fouling, and so on. And in the chemical looping process, the waste is converted in the fuel reactor, but most of the energy actually is released in the air reactor. So here we have around 1,000 degrees, and this air reactor is more or less clean. So we can here use a steam cycle at a rather high temperature without the danger of corrosion and fouling, or with limited danger. So we can increase we can use a very efficient cycle, even higher than conventional waste-to-energy plants, to produce more electricity here. Okay, finally, we're using a metal oxide, and this metal oxide could be reused in some processes like metal and mineral processing industries. Okay, we have some targets for the project. That's capture efficiency 90%, fuel reactor concentration. The CO2 concentration in the fuel reactor could be around 90%. The net electrical efficiency we are aiming for around 35%, including the processing of the CO2. Then the CO2 avoidance costs around 25 euro per ton. Net negative CO2 emissions, because we have the biogenic fraction of the carbon, as explained previously, and to utilize the spent material. So what is the state of the art in chemical looping combustion? There are already results available from our 1 megawatt pilot plant in Darmstadt. We have used this pilot plant to investigate CLC for coal and biomass and mixtures of these. But on the other hand, regarding waste, there is limited information available so far, but waste is actually, let's say, fluidized bed combustion of waste is commercial technology. So we have also some operators of waste, fluidized bed waste combustion plants in our consortium. And so we're combining the knowledge from these two processes into the LOUISE project. Okay, so what are the objectives? These are to demonstrate chemical looping combustion of waste in a realistic environment. We have two plants, one at 150 kilowatt and then the 1 megawatt scale, using ilmenite, which is a natural ore, as an oxygen carrier. We have a lot of experience with this material, so that's why we're going to use this in the first step. We'll develop a basic design of a 10 megawatt demo plant, including the flue gas cleaning and the processing steps. Our aim is also to reduce the CO2 avoidance cost further, using some synergies with other industries, like metal processing industry, by using the oxygen carrier material. And finally, to provide business cases for specific waste-to-energy plants in the 4 different countries of the project. Yeah, here is an overview of the consortium. We have 4 countries: Germany, Norway, Greece, and Turkey. There are a lot of universities, research institutes, but also a lot of industry participation. We have a technology provider here, Dosan. We have specialists in corrosion, Chemin. We have operators of waste-to-energy plant potential end users like Infraserv, Höxt, EEW, also Kvitebjørn. Then we have suppliers of materials like Titania for ilmenite, for example, and Geminur for waste-derived fuels. Kronos as a potential end user of the ilmenite in the ilmenite processing industries, and also Erdemir, which is from the steel industry, and Soka from a refinery in Turkey, and Helector as another potential technology provider. Okay, these are the work packages more closely related to the objectives I just mentioned. The first is pilot testing. The second one is to investigate the interaction of the oxygen carrier with the waste. The third objective is to develop the basic design of the demo plant, and the work package 4 is a business case development, and then we have work package for dissemination and exploitation. The project is an Act 3 project, so it has just started half a year ago, so I'm not able to show you a lot of results. So I show you mostly the plans we are going to do. The first step is the testing in the 150 kilowatt pilot plant at SINTEF in Norway. There have already been some first initial tests for the chemical looping of SRF, and that was actually within another project, a Norwegian-funded project, and these were quite successful from the... And the next step is the one test in the 1 megawatt plant in Darmstadt, using the experience which we gained from the smaller plant. And finally, we are also using some fouling and corrosion probes to investigate how the waste affects the corrosion in the two reactor systems. The work package 2, that's the oxygen carrier material, validation and reuse. Here we are also looking at different oxygen carriers, specifically from Turkey. There are some iron ores from the steel, used for the steel industry, but also byproducts from steel industry, which have a rather low cost then. Then to investigate how these oxygen carriers interact with the waste, specifically looking at these impurities which are contained in the waste. So we have two different kinds of waste we are looking at. First is a typical SRF, a solid recovered fuel that's usually is made from municipal solid waste. So that's a higher calorific value fraction from municipal solid waste, but also looking at a waste from a refinery. And finally, to investigate the reuse of the spent oxygen carrier materials for different processes. One is the titanium production process, but also for the steel industry. For the basic design of a demo plant, we are at the moment developing two kind of models. One is a process model, typically Aspen Plus process model, to investigate the entire process from including also the electricity generation and so on. But also CFD models to look more deep into the fluidized bed reactor systems, and both models are validated by the pilot tests I have shown previously. And these models finally will be then used to design the 10 megawatt demo plant, including fluidized bed reactor system, the flue gas treatment, and also usage of CO2. We have the business case development in a fourth work package. We have defined 4 cases in the 4 different countries. Mainly these are SRF combustion plant, but also the refinery. So we are using, developing concepts and do some life cycle assessment, but also finally the business case development. Cool. That was it for the moment. Thank you very much for your attention, and thanks also to the funding organization.
Thank you so much. Just on time.
Okay,
I'm really impressed by the way you've managed to integrate basic research and the focus towards demo plans. This is really, really good. Absolutely. Okay, you'll be back on stage with Annika later on today. Now we will have 15 minutes break. Use that time to interact and discuss with each other, and be back precisely 10:15. Thank you.